We have learned a lot about the nature of time. We've learned about how time elapses at different rates if you're moving or in a different gravitational field. We've gained insight into trying to understand why the future is different from the past. But the deep questions that continue to puzzle me and many of my colleagues is, what is time? Isaac Newton was one of the first people to try to come to grips with the nature of time. And he kind of took the easy way out. He basically hypothesized that there is this thing called time, and he says that it flows equably in equal intervals, regardless of where you are or what you're doing. He basically introduced the idea of a grand cosmic clock that relentlessly ticks forward moment after moment after moment, kind of dragging us all forward in time at exactly the same rate, squaring his ideas of time with the everyday experience of time. Before Isaac Newton, people basically understood time from their own experience. We all have agreement on what it means to meet at a certain location at a certain moment in time. And so people just took it for granted that there is this quality of the world called time, and it is what allows us to impose an order on our experiences, right? Time is what allows us to talk about past and present and future. And those are useful concepts when we try to make sense of our common experience. We find it very useful to divide time into certain intervals, right? I mean, the Earth, it spins around one rotation in a day. So that's where the notion of breaking time into days comes from. The moon, it has certain phases as it goes in orbit around the Earth, and that's what gives rise to the notion of the lunar calendar, the month. And then, of course, the Earth itself goes around the sun once per year, and that gives us our natural definition of what we mean by a year. And so we use these natural rhythms in our everyday experience to break time down into natural intervals. When Isaac Newton was trying to figure out the basic workings of the universe, he recognized that a key idea is that motion is simply an object occupying different locations over different moments in time. And so his laws of motion that he ultimately developed try to write down a correlation between where something is and when it is at that location. So the great achievement of Isaac Newton was he was able to write down equations that allowed him to predict where the planets should be at any given moment. And the wonderful thing is, Newton made those predictions using mathematics. And then when people looked up into the night sky, the planets, the moon, just at the locations where Newton predicted. That is the triumph of Newton's ability to understand how things move through space over the course of time. When Newton said that time is absolute, he simply meant that it elapses at the same rate for everyone everywhere. According to Einstein, the answer to that question is no. It depends on the motion of the object. That's only true, or approximately true, if you're not moving really quickly, or if you are not in the vicinity of a powerful source of gravitational pull. But if you are, according to Einstein, time is not absolute. Time is relative. When Albert Einstein was about 16 years old, he wondered, what would it be like to travel at the speed of light? You know, imagine that he gets on his bicycle and he zips along at the same speed as light itself. Well, he realized that if he could go at light speed, when he looked over at that beam of light, it would hover right next to him. The light itself would appear stationary. Now, the problem is, when he looked at the mathematics that describes the motion of light, the math does not allow light to be stationary. Light can't hold still. And so Einstein faced this puzzle of trying to square his expectation of how light would look with what the mathematics described in terms of how light itself actually would appear. He came up with a simple sounding idea that is one of the most profound insights in the history of our species. He put forward the notion that the speed of light is constant, a fixed, absolute, changing number. This is so different from any other speed of any object in the world, right? I mean, if I throw a baseball toward you, right, the speed at which you will think the ball is approaching you will depend on whether you're standing still, or if you're moving away, or if you're moving toward the ball. You move toward it, the speed will be faster. You move away, the speed will be diminished. But Einstein said if I replace the baseball with a laser and I fire the laser toward you, regardless of whether you move toward the laser or away, the speed at which it will approach you is one fixed and unchanging number, 299,792,458 meters per second, a fixed, absolute, unchanging speed that is the same regardless of your motion. Speed of light, absolute, constant, unchanging. The idea that the speed of light is constant is so profound because speed is a measure of how far something goes divided by how long it takes it to get there. It therefore is a measure of distance, space, divided by duration, time. And so if the speed of light is behaving weirdly, that must mean that space and time behave weirdly at very high speeds. And this is what intrigued Einstein. And this is what drove him to determine the weird, unexpected qualities of space and time that only emerge at very high speeds. Einstein did his experiments not in the laboratory with equipment, but rather in his brain. He was able to simply think through scenario after scenario, allowing him to extract deep insights into the nature of the world. And then he was able to put mathematics to describe these thought experiments in quantitative detail, allowing him to write down formulae, mathematical equations that describe the new strange properties of space and time. He found that space and time themselves cannot be constant, but rather they must change in exactly the right way so that the ratio, which is what speed is itself constant. And so, if you're talking about space and time in the Einsteinian framework, they become radically unlike what Newton had in mind. For Newton, space and time are absolute. For Albert Einstein, space and time are relative. According to Albert Einstein, if you and I have two wristwatches and they're completely synchronized, I go off into space in this direction and you and I continue to compare the rate at which time elapses on our wristwatches, we will find that they no longer agree. Scientists actually do this. They need to use highly precise atomic clocks. And this was done back in the 70s. Two scientists, they took two atomic clocks, they left one on the tarmac, they put the other in a jet, and they flew that jet around the world, took the clock off the plane and compared it to the clock that they left on the tarmac. And they showed different amounts of elapsed time. And the differences were exactly what the equations of Albert Einstein predicted. So there is no longer a universal notion of now once Albert Einstein gets through with his reworking of the nature of time. In Einstein's general relativity, this is his discovery in 1915, he realized that there's another influence that can affect the passage of time. He basically found that gravity can be thought of as pulling on time, slowing its passage. And so the stronger the gravitational pull you experience, the slower time itself will elapse. In fact, if you're near the edge of a black hole, the gravitational pull there can be so powerful that a clock seems to freeze at a fixed moment in time. Now, these are deep and profound insights, but they do not answer the question that has to do with another quality, a common quality of our experience of time, which is that time seems to move toward the future. It seems to have an arrow from the past toward the future. Where does that arrow of time come from? Entropy is a concept in physics that describes the amount of disorder in a physical system. Now, what in the world does that mean? Let me just give you an example. Imagine a child's bedroom that's completely ordered in the morning, but then in the evening, that bedroom is a total mess because the child has made use of the toys and books and they're all scattered across the room. Now, why is it useful to talk about order and disorder? Well, that example makes clear. It takes much more concerted effort to create an ordered arrangement, and it's very easy to create a disordered arrangement. And because of that, left to their own devices, the room tends to go from order toward disorder. And we call that going from low entropy to high entropy. Everything in the universe tends to go from order toward disorder. I mean, we can even do an example. If we were to take these two liquids, so we have an orderly collection of coffee molecules, an orderly collection of milk molecules, and if we pour the milk into the coffee, we get a mixture, a disorderly mixture in which the milk and coffee molecules intermix among each other. That's going from lower entropy to higher entropy. And that move from order toward disorder, low entropy to high entropy, is something that we recognize throughout the cosmos. So a deep puzzle in physics is that when we look at the fundamental equations that we use to describe the universe, those equations, regardless of whether you're looking at the ones from Newton or from Einstein or from Maxwell's describing the motion of light, all of those equations share the property that they don't distinguish between forward in time and backward in time. And yet our experiences are anything but agnostic when it comes to the direction of time. Everything we experience seems to point from past toward future. How do we explain that? Well, one idea is to use this notion of entropy. What does it mean to go into the future? It means for entropy to increase. And so there was a time when physicists thought that that might be the answer. Where does the arrow of time come from? It comes from the relentless increase in disorder. Perhaps that's what distinguishes the future from the past. So many things in the world appear to be irreversible, happening in one temporal orientation, right? I mean, if I were to take an egg and I smash it on the ground, right, it splattered. None of us have ever seen an egg unsplatter. Why is that? Well, here's the thing. It is the case that entropy increased as the egg splattered. It went from an ordered oval shape to a disordered mess all over the floor. That's the natural progression from order to disorder. But from the standpoint of fundamental physics, if I was to get into the molecules making up the shells and the yolk and the albumin and everything that splattered when the egg splattered on the floor, if I was to reverse all of those motions, then all of those particulate ingredients, they would move toward each other and they would reassemble the egg itself. And so even though it appears to be an irreversible motion from egg to splatter, in principle, that splatter can be undone. It is, according to the laws of physics, reversible. So the arrow of time seems like it might be explained by entropy, but that does not quite work. Because once you recognize that the laws of physics, the fundamental laws that describe how things change, if the laws don't distinguish between forward in time and backward in time, entropy, which relies upon those laws, can't explain it either. So where does the argument break down? If you start from any moment in time, the second law of thermodynamics says that disorder, entropy, should increase toward the future, but it should also increase toward the past. And that symmetry between past and future is what the laws of physics demand. Now, what would that mean? Well, let me give you an example. Imagine you have a partially melted ice cube sitting on a plate. Well, you all know that as you go toward the future, entropy increases, which manifests as the cube becoming ever more melted, ultimately turning into a little puddle. According to the laws of physics, that same progression should hold when going toward the past, which would mean that the partially melted ice cube did not emerge from a yet more solid ice cube, as our intuition and experience suggests, but rather that partially melted ice cube should have begun as a small puddle of water that then coalesced into that partially melted ice cube. And so future and past, according to entropy and the fundamental laws of physics, on completely equal footing, entropy alone, therefore, does not give us the arrow of time. The best way that we have found to get out of this impasse is to hypothesize that the very early universe, the beginning of the universe, must have been a highly ordered configuration, and we have been living through the degradation of that order ever since. And so we hypothesize that the beginning of the universe is what anchors the arrow of time by anchoring entropy at a very low value, by anchoring the universe in a highly ordered configuration. What that would mean is when I drop an egg and it splatters on the floor, the fact that the ordered egg exists at all is a reflection of conditions at the Big Bang itself. If the Big Bang wasn't highly ordered, we would never have ordered objects in the world around us. We would never have ordered eggs that could splatter. And so the arrow of time is anchored. It finds its beginning in the beginning of time itself. So that raises a question, why was the Big Bang so ordered? Answer, I have no idea. Nobody on planet Earth has any idea either. We have ideas that we have thrown around, but there is no consensus on what may have imposed this high degree of order on the Big Bang itself. We have learned an enormous amount about time, both from relativity and from thermodynamics. But if you were to ask me, what actually is time? I still don't really know how to fully answer. Time is a quality of the universe that allows for change. And we notice that time has elapsed by noticing that things have changed. But is that quality of time a fundamental feature of the universe? Or is it something that we humans impose on the external world in order to organize our perceptions of reality? These are questions that are deeply controversial. And even today, we are not convinced that time itself is a fundamental quality of reality. Most theories of physics that we take seriously simply assume the existence of space and the existence of time. But recently, as we have been examining equations of certain ideas coming out of unified theories and string theory, we're beginning to see the glimpse of a realm of reality where time itself has yet to appear, a kind of timeless realm that may be a more fundamental starting point for understanding how the world exists. There was a period in physics where we simply took for granted that time was a fundamental ingredient in any description of reality. My intuition about where our understanding will go is, I think in the future, we're going to have a new formulation of fundamental physics in which time itself does not appear. And instead, we will find that time only emerges in certain environments, certain contexts in which time itself becomes relevant. So rather than time being something we impose from the outside into our equations, my suspicion is that in the future, time will emerge from a more basic starting point, that time itself will be an emergent quality of reality.